Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics in the chapter of pressure in liquids. This exercise was a previous one in the brevet exams in 2013 second session, third exercise. The title of this exercise is Determination of the Density of a Liquid. Consider a tube containing a certain amount of water, figure 1. So they mentioned figure 1, now we can use it. Given that the atmospheric pressure P atmosphere is equal to 76 centimeters of mercury. So notice that here the quantity and the unit are not in agreement because we know that the SI unit of the pressure is given by Newton per meter square or Pascal, whereas centimeter represent the unit of length or height. So from the early beginning we need to rewrite this properly. So because this value has a unit which is centimeter, so it represents the depth or the height, and in particular the atmospheric height. So the atmospheric height is given by 76 centimeters. Knowing that also centimeter is not the SI unit of length, in order to convert from centimeters to meters, we simply divide by 100. Then 76 divided by 100. Then the atmospheric height is given by 0.76 meters. The density of mercury rho Hg is given by 13,600 in the SI. So Hg stands for mercury, 13,600 kilogram per meter cube. And the gravitational field strength is given by G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Notice that till this moment they didn't mention anything about figure 2, then we are not allowed to use it. Now number 1, part A. The two free surfaces of water are at the same horizontal plane. Justify. So always such type of questions are answered using the rule of 3, and the rule of 3 is given by the same liquid at equilibrium and either same pressure or same horizontal level. So since they are telling me the two free surfaces of water are at the same horizontal plane, so here plane means level, so we will eliminate this. Our answer will be, because they are in the same liquid, indeed the points A and B are in the same liquid, which is water, so this is water. And at equilibrium the tube is not moving, and they have the same pressure. Why the 2 points A and B have the same pressure? So notice that the point A is at the free surface of water, so nothing above A is found. So the point A is open to the atmosphere, therefore it's being submitted to the atmospheric pressure. The same goes for the point B. It is at the free surface of water, so nothing is found above the point B, so B is open to the atmosphere, and in particular it's being subjected to the atmospheric pressure. So the points A and B have the same pressure, which is the atmospheric pressure, so they are at in the same liquid at equilibrium and submitted to the atmospheric pressure. For this reason they are in the same horizontal plane or level. Then let's say since the points A and B are in the same liquid, so this liquid is given by water, and the U2 for sure it is at equilibrium. And submitted to the atmospheric pressure. Then A and B are in the same horizontal level or plane. It's the same horizontal plane. And now in part B, calculate in Pascal the value of the pressure at A and that at B, figure 1. So as we have said that A and B are submitted to the atmospheric pressure, So in other words, we need to calculate the atmospheric pressure. Then let's say A and B are submitted to the atmospheric pressure. So in other words, we need to calculate the atmospheric pressure, which is given by P atmosphere. Now the atmospheric pressure is equal to the pressure exerted by, so the atmospheric pressure is equal to the pressure exerted by 76 centimeter column height of mercury. So it's the pressure due to mercury due to a liquid, and we know that the pressure due to a liquid is given by the density of the liquid times G times H. Here, because the liquid we are using it's mercury, so it's the density of mercury times G, and the height is given by 76 centimeter height of mercury. So the atmospheric pressure is equal to the density of mercury, which is rho Hg, multiplied by the value of G, multiplied by the atmospheric height. Now the density of mercury is given by 13,600. In the SI, the value of G is given by 10. And the atmospheric height is given by 0.76 meter. Now plugging this on the calculator, then the value of the atmospheric pressure is given by 103,360. Since everything is expressed in the SI, rho, G and H, so the value of P atmosphere will be in the SI, which is given by Newton per meter square. And another unit for Newton per meter square, which is denoted by Pascal, since here they are telling me calculate in Pascal. So the value of the atmospheric pressure is given by 103,360 Pascal, or in Newton per meter square, it's the same. And now in number 2, we want to determine the density rho prime of a certain liquid L that doesn't mix with water. For this reason, we pour in branch 1 of the tube an amount of oil to a height H is equal to 20 centimeter and of density rho is equal to 900 kilogram per meter cube. So this is the branch 1. We pour in this branch a certain amount of oil of height H is equal to 20 centimeter and the density of oil is given by 900 kilogram per meter cube. So let me write here that the value of H is given by 20 centimeter, knowing that centimeters is not the SI unit of length. So from centimeters to meters we divide by 100, then 20 divided by 100, then the value of H is given by 0.2 meters, and the density of oil is given by 900 kilogram per meter cube. And in branch 2, so we pour also in branch 2 a certain amount of L to a height H prime is equal to 16 centimeters. Then H prime is equal to 16 centimeters, which is given by 16 divided by 100, which is equal to 0.16 meters. Okay, so the surfaces of separation water, oil and water liquid are at the same horizontal plane, figure 2. So they mentioned figure 2, now we can use it. So here they are telling me the surfaces of separation water, oil. So let me say that this is water, this is oil, and this is the liquid L that we wish to determine its density. They are telling me that this is the surface of separation between oil and water, and this is the surface of separation between water and the liquid L. They are telling me that the surfaces of separation water, oil and water liquid are at the same horizontal plane, and this is represented by this dotted line. Okay, now we are in number 2, part A. So determine in Pascal the value of the total pressure at A. So whenever we are interested in determining the pressure, we always look upward. To which pressure the point A is being submitted. So the point A is being submitted to the pressure due to oil and due to the atmospheric pressure. Then let's say that A is submitted to the pressure exerted by oil and to the atmospheric pressure. Then the total pressure at the point A is given by the pressure of oil plus the atmospheric pressure. So notice that the pressure of oil is due to the pressure of a liquid, which is given by the density of the liquid times G times H. Now the density of this liquid, which is oil, is given by rho times the value of G times the depth. The depth here is denoted by H plus P atmosphere. Now the value of rho in the SI is given by 900. The value of G is given by 10 and the value of H is given by 0.2. Plus the atmospheric pressure, which is given by 103,360 in the SI. Now plugging this on the calculator, then it's given by 1800 plus 103,360. And now plugging this on the calculator, then the value of the total pressure at the point A is given by 105,160. Since everything is expressed in the SI, this and this, then the value of the pressure at the point A, the total pressure is in the SI, which is given by Newton per meter square. Another unit for Newton per meter square, which is the Pascal. So it's given by 105,160 Pascal. So the total pressure at the point A is given by 105,160 Pascal. So the total pressure at the point A is given by this value. Now in part B, they are telling me deduce in Pascal the value of the total pressure at point B, and by deduce it means that we need to use the previous part. So notice that here the points A and B have the same pressure because due to the simple reason which is given by the rule of 3. So the rule of 3 says that same liquid, at equilibrium, and either we say same pressure or same horizontal level. So since we are interested in deducing the value of the pressure at the point B, which is equal to the pressure at the point A, so we need to say that the pressure at the point A is equal to the pressure at the point B. So same pressure, we will eliminate this. Then we must say first that the points A and B are at the same liquid at equilibrium and the same horizontal level. So they are in the same horizontal level because here they mention in the text that the surfaces of separation water, oil and water liquid are at the same horizontal plane. So this is okay. Now indeed the YouTube is at equilibrium, so this is done. Now it's left to say that the points A and B are the same liquid. So whenever we need to justify that the points A and B, so if we need to determine here, for example, the point A is between oil and water. So whenever we need to determine whether the point A is in which liquid, we always look downward. So below the point A there is water, so the point A is in water, and the point B is between the liquid L and water. So whenever we need to determine the point B is in which liquid, we always look downward, so the point B is in water. Now let's say since A and B are in water, which is the same liquid at equilibrium, and in the same horizontal level, then A and B are submitted to the same pressure. Then we can say that the total pressure at the point A is equal to the total pressure at the point B. So we have that the pressure at the point A is equal to the pressure at the point B. But we know that the value of the pressure at the point A is given by 105,160 Pascal. Then in this case, the pressure at the point B is given by 105,160 Pascal. Now in part C, give the expression of the total pressure at B as function of rho prime. So here we need to determine the value of the pressure at the point B as function of rho prime. So we are asked to determine the expression of the total pressure at the point B as function of rho prime, and we are not asked to calculate or to determine the numerical value of the pressure at the point B. So since we are interested in determining the pressure, we always look upwards. So above the point B we have the liquid L. So we are interested in determining the total pressure. Then let's say that the point B is submitted to the pressure of L. And moreover, above L we have the atmospheric pressure. And to the atmospheric pressure. And now we are ready to calculate the pressure at the point B, the total pressure. So recall that they usually give half a mark for this statement. So the pressure at the point B is given by the pressure due to the liquid L plus the atmospheric pressure. Now because L represents a liquid, so its pressure is given by the density of the liquid times G times H. Now the density of this liquid is denoted by rho L, rho prime. So this is rho prime times G times the depth or the height, which is denoted by H prime, plus the atmospheric pressure. Knowing that we need to determine the total pressure at the point B as function of rho prime, so we keep rho prime as a variable. Knowing that we are interested in determining PB, so rho prime times the value of G is given by 10 and the value of H prime is given by 1.6 in the SI, sorry, 0.16. So this is the value of H prime, plus the atmospheric pressure, which is given by 103,360. Now 10 multiplied by 0.16, which is given by 1.6 rho prime, plus 103,360. Then the total pressure at the point B as function of rho prime is given by 1.6 rho prime plus 103,360. So notice that here the value or the expression of B doesn't carry any unit, so it's more convenient when we have determined the expression of a certain quantity in terms of another quantity. It's better not to include any unit. And now in part D, deduce the value of rho prime, and by deduce it means that we need to use the part just previously before. In part C we have determined the value of PB as function of rho prime, and knowing that we know the numerical value of PB, so let's say that PB is equal to PB. On one side we know the expression of PB in terms of rho prime, which is given by 1.6 rho prime plus 103,360, and on the other side we have the numerical value of PB, which is given by 105,160, knowing that we are interested in determining rho prime. So what's the type of this equation? This is a linear equation and one unknown. The unknown is given by rho prime. So how do you solve this equation? We put rho prime on one side and all the other numbers on the other side. So 1.6 rho prime is equal to 105,160. Now dragging this number to the right hand side, it will gain a minus sign. So it is minus 103,360. So 1.6 rho prime is equal to, now plugging this on the calculator, then the value of 1.6 rho prime is given by 1800. Let me continue this here. So 1.6 rho prime is equal to 1800. Notice that yet we didn't answer the question because we are interested in determining the value of rho prime. We have determined 1.6 rho prime. So we need to get rid of 1.6. We divide both sides by 1.6. So this goes out with this. Then the value of rho prime is given by this fraction. Plugging this fraction on the calculator, then the value of rho prime is given by 1125 kilogram per meter cube. Why kilogram per meter cube? Because everything in the SI and the SI unit of rho prime is given by kilogram per meter cube. Unit of density, SI unit of density. So the density of the liquid L is given by 1125 kilogram per meter cube. Let me write here that rho prime is equal to 1125 kilogram per meter cube. And the value of rho is given by 900 kilogram per meter cube. And here let me say the following. So notice, and this is water, and the density of water is given by 1000 kilogram per meter cube. So notice that in this case, these two liquids that are given by oil and the liquid L are floating at the surface of water. And we expect that both densities must be less than the density of water. So let's discuss the density of the oil. So the density of oil is given by 900 kilogram per meter cube, and indeed it's less than the density of water, so we expect that oil will float on the surface of water. However, here the density rho prime is given by 1125 kilogram per meter cube, which is more dense than water. So the density of this liquid is more dense water. So how come this liquid is floating at the surface of water? So this proves the following fact, that there is something wrong in the structure of this exercise. And by this we have finished solving this exercise. Hope it was beneficial for you guys out there watching it, and see you soon in another one.